Recording. Check one, check two. Hello, hello, hello. Hopefully you all can hear me. Yeah, awesome. All right. Hi. This is November 17th, 2 o'clock Eastern, Module 7 live session. It should be a fun week. I was laughing that, of course, the YouTube auto clipped the like Fox News like thing as the thumbnail for my video. But hopefully, we had a chance to catch up with the live session last week. We had some good conversations around color theory, dashboard design, what makes a good visualization versus a bad visualization. I love geeking out on some of this stuff just because it's so different than what data science normally is with data wrangling and thinking logically and building predictive models and looking for relationships and things. So definitely don't forget the artistic side and the storytelling side of data analytics and data science. Coming into this week, I want to go over a lot of content in the live session here. Even though the actual media sets themselves are fairly short and there's only a couple of labs, there are a lot of big ideas introduced that we're going to go ham on next week. For those of you watching, Module 8 is a bit of a doozy. So good luck next week. By just a bit of a doozy, I mean that it has a lot of content. If you go down to the labs, you can see it's like 8.1 all the way through 8.8. So there's a lot of notebooks, a lot of code to go through. So I want to give you a proper foundation today and this week into kind of what you're going to be doing next week. So both this week and next week is machine learning. We talked about and we introduced machine learning at a very high level a couple of weeks ago in week 5. This week, we're introducing regression versus classification and doing that in terms of linear modeling. I am also going to show a random forest today. And then we also talked about in week 7, you'll also talk a lot about the full ML life cycle or the machine learning workflow. So in industry, we call this ML ops or ML operations. How do we start thinking about a predictive model as a data product as opposed to just like a one-off equation? So it's really interesting, right? I think where data science and analytics came from. Um, it came from like white papers. So like I don't even know what I was gonna Google there. But maybe your end result would be kind of a document that you would submit to the Science Nature magazine, and you would include kind of this whole study of your analysis. I watched like this space documentary the other day. So it's like maybe it's like this analysis about all the planets moving around the sun and comets, and you made an equation to predict the next time Halley's Comet's going to bypass the Earth or something. And so no one actually uses the equation. It's just sitting there in this white paper as a document, right? Just that's kind of the static thing. Businesses and data-driven organizations started moving to compete on analytics and to compete with predictive analytics specifically. We started needing to take these equations that maybe you draft once or a model that you define once, but we need to start using it every single day. And what ends up happening is once you start utilizing models every single day, you start to notice things such as data drift, model degradation. Your model gets worse over time as lifestyles and fads and things change as well. So for example, like let's say you want to build a model to predict how many fidget spinners you're going to sell, right? In 2020, 2021, that model, if that's what your model was trained on, is going to predict that we're going to sell a whole bunch of fidget spinners every single day. But if you use that model trained on 2021 data to predict 2025's holiday season rush for fidget spinners, it's probably not going to be a very good model, right? Fads and trends are different. When I worked in baseball, this was a pretty big deal. That was a juiced ball 2021. Let me see if I can find this graph. It's pretty funny. Um, I'll say that was a good graph about like the number of home runs that was like hit per year. Uh, anyway, long story. Let's see if I can find. Let's see, home runs by year. Let's see if I can just find a recent one. Juice balls. Yeah, this is kind of a go. If you zoom in on the other side of the graph, I wish there's a basic one. I'm just like, I want to see the last like 10 years. Yeah, I guess that's probably the best we're gonna get. Um, Let me go back to whatever. I should have been more prepared, but I'm looking at this graph right here. So what do you want to look at is that we had this giant peak in like 2021 and then like home runs kind of plummeted again. So basically what ended up happening is Major League Baseball had like a different type of ball that they actually put into production. And this ball was bouncier. Basically, it made it so that when you hit the ball, it was gonna tr the same exact swing, the same exact strength and angle. The ball just by itself would travel an extra few feet further. And so this meant there were more home runs than people expected in 2021. So the idea then is if I train a model to predict how many home runs someone is going to hit in 2025, and I train that data on data from 2021, we have data drift, right? The ball is different in 2025, so I shouldn't use a predictive model that was trained on stale or old obsolete data. So the big idea of this is ML and modeling and predictive modeling has moved from being a static product. You train a model once, you call it a day, and now it's moved into a dynamic data product, right? And with dynamic data products, we need to have a strong control around the model lifecycle. So there's a few videos of this in the media sets this week, but it's also going to be something that we'll talk about a lot. I'll probably just talk about it now, honestly. So let me find a diagram of it. I think I shared this diagram uh, in one of my recap videos. Let me open image in new tab. It's actually from Databricks. Nice. Yeah, so this is a pretty fun like graph. I'll share this documentation as well. But the idea is, again, in the olden days, you would do your EDA. Some of this sounds familiar. Do your data prep, your data pre-processing, do your data cleaning, train your model, develop your model, train your model, and then call it a day. So this is where traditional data science ended a few years ago, a decade ago. So now that we're starting to use models as dynamic data products, ever-changing data products, we need to figure out how to deploy our model into a production system, right? Every day I want to make new predictions on how many home runs I'm going to hit, or how many fidget spinner widgets I'm going to sell. So we have to then deploy our model, make those inferences every day. And this is where there's an interesting handoff because sometimes these inferences can actually be a data engineering workflow, right? If your data engineer is the one ingesting data every night at 2 in the morning and then running it through the model, this should just be a step in the data engineering pipeline. So make your predictions and then monitor the model, right? Monitor the model's performance. Look for when you need to retrain the model. Look for degradation in the model. Look for data drift in your data sets. If your model no longer represents the data that's coming in, then you're not going to be able to make accurate predictions. Remember, all a model is, whether it's a linear model, a random forest, a neural network, or even a generative AI model, all it is a pattern recognition algorithm. It's looking for patterns in its training data, using those patterns then to then predict something in the future. So if your model was trained on something irrelevant or not relevant to the current situation, then obviously the patterns that it finds are not going to be positive of patterns that you may see in the real world, right? That's why when like ChatGPT first came out, it didn't know anything after 2019 because it was trained up to 2019 and at that point did not have the functionality to go search the internet for new behaviors, right? So that's kind of again like common thing. If your model is only trained on data from 2019, you're trying to make a prediction in 2025, you got to make sure that 2019 is representative of 2025. So this is a very common pitfall you see. I see this a lot, especially in the financial sector, where just because you assume these trends kind of held 10, 15 years ago doesn't mean that's currently trends in the current day. There was a big conversation on like financial Twitter and podcasts recently about the guy from The Big Short, who obviously got famous for shorting the housing market and then making a bunch of money after the housing crash in 2008. Great movie. Go watch it if you haven't already. But it was recently kind of discussed about like around the AI bubble and everything is like things that probably should eventually collapse or like securities that should probably not be as valued as high as they are. They're not, the market's not reacting in the same way that it did in 2008. And so again, if you're building a model or trying to make predictions on investment stocks based on what you thought like investors were using to make decisions in 2008, it may not track in the present day. So again, all long-winded story to say your model is only as good as the data you give it. And as we start thinking about models as ever evolving data products like dashboards and data sets that need to be updated every single time, we have to start integrating strong controls and ML operations and data ops into it. You'll see ML ops is a collaborative function between data scientists, data engineering, DevOps, and IT. All right. With that all being said, let's what do I want to cover today? I want to go over regression versus classification. We already reviewed regression metrics such as MSE, MA, and R squared. We're going to spend a decent chunk of time over the next hour on classification models. And I want to go over kind of what is a classification model and the metrics used to evaluate classification models. And then I want to also show a scikit-learn pipeline, which I think we'll actually do more in module 8, but hopefully should be a good time if we have time to do that. If you're keeping up with the documentation, um, there's a lot, hopefully, that you're able to see through scikit-learn. Regression, we're going to dive more into this. Classification, that's what we're going to spend the meat of the lecture on today. Clustering and dimensionality reduction, we're going to introduce in module 8. And then also grid search we'll do in module 8. And then pre-processing, we've already done some of that in week 5. We're going to do some more of that today as well. How do we clean and prepare our data for machine learning algorithms? All right, feel free to drop questions in the Zoom chat. Karen is monitoring that, and I will also kind of answer things as we go. All right, so I'm gonna try and go through all 3 labs just because they're all pretty short here. So let's go to 7.3 first. In 7.3, we have kind of a warm-up lab, so we'll start with 7.3.2. In this lab, this is a warm-up based on what we did in week 5. Honestly, both 7.3.2 and 7.3.3 are both kind of warm-ups. There's not too much difference here. But let's first kind of go back to a machine learning problem, right? Or I like to call it predictive analytics because some people yell at me that linear regression is not machine learning when I do believe it is. But anyway, the whole idea with predictive analytics, figure out what you want to predict and then figure out the features that you want to use to help predict things. And then all that the model does at the end of the day, it identifies patterns in your features that correlate with hopefully predictions in the target. And it's a lot easier to think about that paradigm with linear or mathematical models because we can actually quantify things like correlation and use correlative features to predict a target and then define that with a single line or an equation. Remember, linear models are just one algorithm family. There are multiple types of algorithm families we'll talk about over the next couple of weeks. Linear models, tree-based models, such as your random forest, XGBoost, whatever, and then your neural networks, which also include generative AI models as well. Those are going to be your 3 model families. All 3 model families can solve regression and classification problems. Remember, a regression problem predicts a continuous numeric variable, such as number of home runs, stock price of NVIDIA, whatever. A classification model, which we'll show some examples of here later, predicts a category, or more precisely, it predicts the probability of belonging to a category. So common examples is predicting the probability of a hit, yes or no. Is this ball going to be a home run, yes or no? I'm showing some other class. What are some other classification ones on the top of my head? I'm on a big sports kick right now. What do you got, Karen? For oh, cat or dog? What's some? Oh, spam or not spam? That's some easy ones. Uh, yeah. What's some other good ones? I don't know. Either way, it's so room is occupied, yes or no. Healthcare. Am I going to be have diabetes? Yes or no. Do I have high blood pressure? Yes or no. Do I have COVID? Yes or no. Um, I think that's kind of the more classical examples. And then yeah, regression model would be like predicting housing prices or something. So when we dive into the content today, we're going to be doing linear models. So there's one quick thing just to highlight because it's going to come up later. A logistic regression model is a linear model, but it does classification. It's just really poorly named. So a logistic regression does not do regression in the way that I'm talking about it. It's a linear model for classification. Contrast that to linear regression or OLS. A linear regression is a linear model for regression. And you can even see kind of how scikit-learn organizes this, right? We're importing algorithms from the linear model family the linear model for regression is linear regression. There are other examples, including elastic net and ridge, that I'll probably touch on today as well. But that's kind of the big idea. Logistic is the main linear model for classification. Yeah, that's a good idea. Maybe we'll touch on some of those other advanced models here as well. So let's just do our quick warm up, just so that we're all kind of on board with what we're going to do over the next hour or so. Load in some libraries. Again, probably doesn't need to be run, but whatever. We'll let that go. And then we're going to load in the data set. We're going to be looking at, oh yeah, fuel consumption. And all these notebooks have already been run on and backed up on my GitHub if you need to reference them on Colab or anything. But I'm going to do some live stuff here today, so that should be fun. That's the point, right? All right, so here's what our data looks like. We have all these cars, and we want to be able to predict, I think we're going to predict emissions or something. What are we predicting here? CO2, I think we're going to be predicting CO2 emissions. Yeah, so we're going to try and predict CO2 emissions from these specs about our car. To keep it easy, we're going to not worry about the categorical data yet. We'll do some more of that next week. But we're just going to keep our numeric data, and we're going to try and predict carbon emissions. So first, we do some EDA, exploratory analysis. We look at our features. What I would then probably do from here is I'm gonna add a new cell, insert cell below, boom. What we can then do is look at the correlations. And if I look at the correlations, I don't know why. Oh, I kept model year. We can look at is we can start looking at the correlations of my features against CO2 emissions. And we can actually see that they're all pretty strong. Um, all have zero 0.8 all the way up to a negative 0.9. That's just a strong negative correlation, which basically means that the better your miles per gallon, the lower your carbon emissions, which makes sense, right? If you're getting like 40 miles per gallon, you're probably emitting less stuff out of your exhaust. Contrast that to like your fuel consumption. The more fuel you use, the bigger your engine, the bigger your cylinders. All those are positive correlations. The bigger your engine, the more emissions you'll have. So again, this all kind of makes sense to me. So this is typically where we start for feature selection. The other one I'm looking at is fuel consumption, city, highway, and combined, right? As well as combined miles per gallon. These are all basically the same feature. And if I actually look at their correlations to each other, right, 1, 96, 99, they're all very, very strongly correlated. In the industry, we call this multi-correlation, which means that a feature is correlated to another feature. Fun fact, in linear regression, this actually violates an assumption. Let me pull up the assumptions of linear regression. One of the assumptions of linear regression is no multicollinearity. It's the idea is that we want our features to be independent. We want them to be not too highly correlated with each other. So it's best practice, especially with linear models, to remove highly correlated features. And if you're curious, we can actually visualize this because I hate looking at numbers. Uh, and don't worry, I'll upload all this to my GitHub afterwards. Oh my God, it doesn't import pip install Seaborn. Whatever. I guess we're stuck looking at numbers for right now. But yeah, that's kind of the big idea. We want to that's how we selected these features. We selected these features by removing the features that suffer from multicollinearity and picking the features that correlate really well with CO2 emissions. And if you're wondering why model year wasn't used, we can actually do a quick, we actually did the describe. If you look at it, every single value is 2014. So there's no variance in our model year. And because there's no variance, it's not going to be a very good predictive feature, right? If every car is 2014, it's not going to help predict CO2 emissions. Exercise for the reader, pull in more modern data, and I would bet that cars made in 2025 have a lower CO2 emission than cars built in 1986, right? All right, so now that we've identified our features, we're going to select them. And from here, we can do some more data analysis. Again, not only for our linear models do we want to make sure they have no multicollinearity, we also assume that our features are fairly normally distributed. So we like looking at the histograms of our features to make sure that they are approximately normalized. And honestly, this looks pretty good. Remember, normal just means a bell curve. Engine looks pretty bell curvy. Fuel consumption and cylinders, they all look pretty bell curvy. So I think that looks good to me. From here, we can then create a scatter plot. And what we're looking at is the correlations. And what's really interesting here is that there's actually looks to be like three different types of cars in my data set. We have three kind of distinct lines that kind of represent the three types of cars that are in our data. So maybe this would be like midsize SUV and compact midsize SUV. So if we could have isolated the type of car, that could have probably been a pretty good feature. And as we look at some of our other ones, we'll see that engine size is also pretty strongly correlated to CO2 emissions. And it wants us to do the cylinder one next. So we'll plop that in here as well. So a big idea in our warm up so far, feature selection, right? How do we make sure we are pulling in correlative features? Next, we're going to just train a quick model. I'm going to fly through this so I can jump to the multiple linear regression. Um, Yeah, actually, well, I may do this twice. So let's load in our train and test set. So we're splitting our data. So we train our data and evaluate our model on unseen data. So we should have, I don't know, 147. I think we have 1,000 rows. So I think it's about 147 rows that we held out. I think it's a typo too. I think it should be N X train, Y train, and then X test, Y test. Yeah, 214. So we have 214 rows of data that our model won't see that we're going to hopefully use to evaluate our model performance. So and now we get into our model training. Notice for this case, my model training is only engine. I'm not using any other feature, just the engine size. So we can train our model and we end up with this model. CO2 consumption, CO2 emissions is equal to 126.3 plus 39 times whatever your engine size is. And that's our line of best fit. We can visualize that line of best fit. Again, this is on our training data. We can see our line of best fit there. And remember, when we start evaluating regression models, we're going to be evaluating models based off of the residual, which is a vocab word from week 5. The residual, all it looks at is how far is the actual data point from your prediction? How bad is your prediction, right? So that difference is known as the residual. So when we start calculating things such as mean absolute error, mean squared error, even R squared, Those are all derived from this one simple metric known as the residual. And here we go. We're looking at our test data. And based on our test data, how good is our model? And we can see that it's all right. R squared is 0.76 and a mean absolute error of 24. So on average, we're off by about 24 carbon emissions, whatever that is. And for those reading, for those astute readers, the 0.76 should just be the correlation of engine size. Or it should be close because I guess it's only on the train data. But if I go to engine size, my correlation is 0.874. If I square that number, it should be really close to this because I'm only using that one value. Yeah, so 0.76. So again, life checks out, math works, great. Galileo was doing this in the 1600s. For these, I'm probably going to skip over these practice exercises because they're not too relevant, but I definitely recommend you doing them on your own time, and you have all the solutions here if you want to. Basically, what I want you to do is to retrain your model using fuel consumption instead of engine size. But I'm going to skip over to the multiple linear regression because we're going to use all of the features instead of just the of one feature. So remember, the difference between a simple linear regression model and a multiple linear regression model is that we use multiple features to predict a target. In almost 99% of your modeling projects in the future, you'll be using more than one feature to predict your target. So this is really kind of the core example here that I want to make sure that we have. I'm also going to pip install Seaborn here at the top just to make sure that we have it up and ready. And if you're following along in the media sets, this is 7.3.3, the multiple linear regression. So the simple linear regression is kind of your hello world introduction. And then the multiple linear regression is the first example that I want to go through. So what I want to show in this is kind of what the end-to-end life cycle would look like if I have a regression model that I want to build out. So we're going to run through the notebook, and then I'm going to add some stuff at the end on how we could actually make this a full end-to-end kind of machine learning pipeline. So here's our data set. It's the exact same data set. And if we drop, yeah, we keep the make model vehicle class. Let me do a quick check here. I want to insert cell above. Let me do df dot, I use value counts. I'm gonna select all this. I think these are all my categorical columns. But let me select these, and then what I'm gonna do is a dot value counts on them. Oh God, that's not what I want. Stop, stop, stop. I'm busting my cell. I'm gonna pop over to ChatGPT. Help me get val counts for each. It's gonna loop through the freaking list, isn't it? It's gonna loop through the list and print out the value count. Unless ChatGPT is offline right now. And I'm all about coding with AI these days. Yeah, loop. Oh my God, how annoying. It's fine. It'll work. Let's plop this in here. Yeah, so what we're looking at is what I'm looking at is the value counts. So when we're thinking about using categorical data in our model, we want to make sure that there's enough signal in it, right? So you don't want to have too many individual categories, and you also want to make sure there's not that many categories with very few observations, right? So we have 663 different models of car. So that's a lot. We're not going to be able to, that's not going to be very signal in pattern recognition. Same thing with the make. There's a lot of different car manufacturers here. Probably not going to be too useful, especially some with very small observations. Probably not useful to bring in either of those either. Vehicle class, there's actually not that many here. So and we have some with a lot of observations. So this actually might be pretty good. Kind of what I was talking about, right? It looks like we have three different types of cars, your SUV, your compact, and midsize. And if I had more time, I'd probably go back through and clean up the rest of these to all be like compact or SUV or something. Transmission also looks like it could be useful. We have not that many, and we have some up here at the top that have some strong signal. And then fuel type. I just don't know what fuel type is. So I'm actually going to keep vehicle class. So I'm actually going to change this cell, and I'm going to not drop the vehicle class because I think it'll be useful. Exercise for the reader. You could probably keep transmission as well if you wanted. All right, so now that we've figured out why we're dropping these useless columns, let's look at our correlation. Again, it's kind of what we looked at earlier. Because I kept vehicle class, I have to do this numeric only equals true to keep the numeric features. And like I said, we can actually visualize this. We can do a say import Seaborn and then visualize it. So it should look something like this if all goes well. Nice. So what we can see here is that with CO2 emissions, everything that's lightly colored beige correlates really well with it. And so we do see a lot of that. And then looking in the middle in my graph, we also see kind of these really strong beige, which again correlates to really strong correlation between fuel city city, fuel consumption highway, and the combination, as well as kind of with the miles per gallon. So again, we've figured out why we don't need all four of those. We want to remove the multi-correlation. Uh, Engine size and cylinders are also pretty highly correlated. I don't know if I believe that. Let me move a new cell up. Let me just look at my correlations. I guess they are. Engine size and cylinders are also really strongly correlated. And because engine size is more correlated to the target, that's the one they're keeping. That's why we're dropping cylinders, and then we're dropping the other three and keeping the miles per gallon combination. Cool. So let's drop those other columns that we don't need. And if we look at our data, we should just be left with two features that are numeric, one feature that is a category, and then our target, which is CO2 emissions. Um, cool. And then it's gonna be mad at me that I have vehicle class. So let me actually just I'm gonna save that off as a different whoops, move that up. I'm gonna create a new data frame here called df orig equals df.copy. And then I'm going to drop vehicle class. Basically, we're going to come back to vehicle class later. I hate this stupid autocomplete. All right, let's see if that worked. If I look at my, great. And if I look at my data frame now, I should only have my two numeric fields and the target. So the rest of this code should now run. All we're doing here is they're looking at this data, which I kind of laughed at. This is such an obnoxious way of writing that code. You could just use Seaborn with a pair plot to do the exact same thing, and you get a much better looking graph. What is this autocomplete? So in all that we're looking at here are the distributions, right? So again, we want our numeric features to be normally distributed, which they are, and we want to make sure that they have some correlation to the target. If I look at the graphs like down here, we see that we have a strong positive relationship. And if I move up a little bit, um, we'll see that with engine size and or the other one, We also have some pretty strong correlations here. So this all looks good to me. It looks like we also have some logarithmic patterns here to identify, which means like no matter how good your fuel consumption gets, like you'll never be that to zero CO2 emissions. So that's like the non-linear relationship. That's like this little logarithmic approach. But we'll leave that as an exercise for the reader to explore later. All right, so let's have a look at our data. And again, the reasoning, if you want for that, is because of the different types of cars, which I'll come back to in a sec. All right, so let's do our pre-processing. For pre-processing, for our data cleaning, we want to make sure that we have no null data. Remember, that's called data imputation, as well as we want to use a scalar to standardize all of our numeric data so they're on the same magnitude. So we can do that here. And if we look at what our data looks like, you can see that we should have the same standard deviation. We go fit everything with a mean of 0 and a standard deviation of 1. And all of my values should be between -5 and 5. So all my features are now standardized to be on the same range. Again, the reason why we do that, if I look at my data up here, my engine size goes from like 1, 2, 3, 4, 5, but my miles per gallon goes from like 10 all the way up to 50. So those are different ranges. So if you think about a linear model, it's y equals mx plus b. So we're going to be multiplying these values by different coefficients. So if my values are on different ranges, it means my coefficients are going to fluctuate pretty wildly. And it's just it's not as clean and organized in helping your model identify patterns. So we like to standardize our numeric data to just make it a little bit cleaner and make the patterns a little more relevant and try and reduce the amount of noise in our data set that bleeds into the model. We also talked about standardization in week 5 as well. And now that we have our train test split, we can build a linear regression model. So here we go. Here's what one looks like. And then notice we now have the two coefficients to kind of multiply against each other. We can even look at what it looks like on the unstandardized feature space. So notice that all my values kind of vary a lot more wildly once we kind of standardize everything back. Again, this is kind of not nearly as relevant. Last thing we're doing, because we have 3 features, we have 2 features in the target. We can visualize this in a 3-dimensional space. I think this is kind of a fun graph, but doesn't really mean anything to me. Instead, what we're looking at is how do each of my individual features relate to the target. And we can see, like, again, it does pretty good. We probably need to have some more nonlinear work done here, or use a model that allows for nonlinearity, like a polynomial regression or a random forest to look at that. All right, let me fly through this because I want to actually get to the meat of what I want to show here. All that we want to do is, what are we doing here? Determine and print the parameters. We already did all this. Oh, they're only doing this as a simple regression. So this is only looking at engine size, which is kind of annoying. So with just engine size, this is what the equation looks like. With what the plot looks like, it'll look something like this. And again, we've seen this graph a bunch of times. And then same thing for how it looks against the test sets. Boom. And now we can do the same thing, but just for fuel consumption. I don't know why they're making you do simple linear regression here when you just did that in the last notebook. But let's get to the meat of the stuff. All right, so the beautiful thing about kind of scikit-learn and linear modeling is that we can start standardizing things. So let's kind of get into the meat of what we want to do here. So when we have our data set, I'm going to go back to my DF original data set. So we've already walked through kind of why we selected this feature. Feature selection is a pretty important part, but we're going to keep it like this. What I like to do then is look at the like .info for null values, and then the .describe for my numeric features. So looking at these two outputs, we can have a couple. Let's start with our pre-processing notes. So that's our data cleaning, our data prep. So looking at my pre-processing, first thing I'm looking at is imputation. Do I have to deal with null values? And that answer is no, we have no null values. So that's great, right? All my info here, we all have, oh, this is df rig. We shouldn't have any null values in my data set. The second thing we have to look at is scaling. Do we need to deal with scaling? And that answer is yes. So we can identify why we need to use a scalar. I'm looking at the average, right? I'm looking at the min, and I'm looking at the max, right? I'm looking at my data distributions. So I'm looking at scaling here. These aren't that bad. I've seen way worse, but these are obviously on different scales, right? One of them goes from 1 to 9. The other one goes from 11 to 60. So we should probably standardize that to be on the same scale. So yes, we need a scalar so features are on the same scale. And then the last thing I have to deal, I usually have for pre-processing is data types, or I call this encoding. Do I need to encode any non-numeric features? And that answer is yes. Vehicle class is a string, is a category. So now we can start making our pre-processing steps. We need to first do an imputer if needed. Then we need to scale our data. I'm gonna use a standard scalar. And then we need to encode using one-hot encoding or dummy variable, or indicator variables, which we also introduced back in week 5 to basically make our full data set. So I'm going to call this my numeric features are going to be equal to fuel consum. I wish I'm just going to copy that. Too lazy to type it out. My other one is engine size, and my last one is, and then my, oh my God, I hate this autocomplete. Cat features. My categorical features is just, sorry, Karen, go ahead.
No.
Vehicle class. And then my target is going to be CO2 emissions. And then I'm going to go to ChatGPT because I'm lazy. And I'm going to be like, yo, here is my columns. I want a scikit-learn pre-processing line with imputer, scalar, and encode. Hopefully it throws me some code real quick. I had one of these done on my GitHub somewhere, but it wasn't in IBM. And apparently everyone's using ChatGPT these days. Love it. Love it. Um, cool. That's exactly what I want. Great job, scikit-learn. So one of the beautiful things here, what I want to review is this idea of a reproducible pipeline, right? So what scikit-learn provides are these helper functions to start bundling things up together. So you can kind of see when we start training our models, we're going to take our data, we're going to impute it for null values, scale it for our numerics. For our categorical data, we're going to impute it using the mode, and then encode them using our one-hot encoder or our dummy variables. And then we can bundle both of these pipelines up together into this pre-processor. So this is beautiful. Great job, ChatGPT. And then at the end of where this comes into really relevancy is when we start adding in models. So in this case, what I'm doing here is we're loading in the linear regression algorithm. We now attach that as a step in my pipeline, and now we're able to train the model. So let me actually go grab my data set, and we're going to bundle this up into a handy dandy function and then reuse that function a whole bunch of times and see how things go. Where is my train test split? There you are. Hopefully ChatGPT can do all this for me as well. Um, Cool. So let's do something like it'll look something like this. Let's import some other algorithms. Elastic net. Oh my God. Let's do ridge regression. Is it just ridge? Hopefully that's it. And then we don't need my X and Y. All right, and then I'm just gonna ask ChatGPT again. So,
Alexander,
yeah, what's up?
having ChatGPT do it and copy and pasting it is so in 2024.
I know I have Cursor installed, but I didn't want to show everyone how to do that. Help me try make a function to try different models. Print the MSE MAR squared for both the train sets and test sets. Um, and show the predicted versus actual plots. And we'll wait for this to go through. I wrote this function manually a long time ago, and then I was yeah, there we go. What are we doing? Take in your model. I'm going to define the preprocessor inside the function, and then fit the model, generate your metrics, generate your evaluative plots, and then return everything else. Alrighty, let's grab that over here. I'm gonna shove that in here. Like I said, this whole preprocessor, I'm actually, what's this model class situation? We don't need the model class or the model name. That's dumb. Let's get rid of that. We don't need the model name. We don't need the preprocessor. And let's just bring all this up. Boom. I don't care about the model quarks either. All right, out of my life. All right, cool. So let's make this, let's clean this all up. All I'm doing in here is shoving in my pipeline. So we're going to pass in our data frame. Um, we have our features already. We're going to do our pipeline to pre-process everything. We're not going to bother with any model quarks. And then we're going to pass in our model. Looks good to me. Fit the model, generate our predictions, get our metrics, plot the results, and then hopefully this actual works. We don't have this model name thing, and I think that looks fine. Missing a closing parenthesis. Uh-oh. Oh, boom. Sweet. So let's see how this works. So again, big idea of what we're trying to do is we're trying to make something reusable. So I have my data frame, right? We can define a model. So let's do our model equals a linear regression model. The idea is that we should hopefully just be able to run our data and our model through this handy dandy function. So let's first get the data. I guess we don't need our DF, right? I don't know why I added that in. I'm panicking doing things live. We already have our data set. So let me grab the X train, Y train of our data frame. And then I'll take a breath and actually look at this code. That's what I need. Hmm. How do we do this? X equals df orig dot drop columns equals, what's my target? Oh, we already put in our, and then the uh, target. And then we X train test split X and Y. Lovely. And then we should be able to run this all the way through my model if all goes well. We'll see what all the red lines are for. Linear regression is not defined. What do you mean it's not defined? Let me grab that again. Could have sworn I already ran this. Whatever. Let's load in our ridge, elastic net. Great. What's the other one? Lasso. Great. So let's see how this works. Linear regression. Womp womp. The vehicle class is one word. Model name. Where do I have model name again? Out of my life. Great. So I'm just going to add in I wanted to add in like a blank. Let's see if that works. No. Da.
Doing?
No, I'm doing something dumb. I'm trying to add in like a spacer between my oh, it's not gonna like it. Whatever, we won't add the spacer, it's fine. Cursor would have added the spacer for me. But anyway, if we're looking at our linear regression model, we can see that our linear regression model does really good here. It's not overfitting. It has an R squared value pretty close to zero point 0.9, and we have this pretty strong linear trend between our predicted and actual, which again is if I'm predicting how much carbon emissions I'm going to emit, I want to actually compare that to the actual value. So again, similar things with the residual. So what we're looking at here is that is a pretty good. We're not overfitting. We don't have patterns in the residuals. These outputs look pretty solid to me. We can even see kind of our full pipeline down here for what it's doing. We can then reproduce the beauty of this, though, and the beauty of scikit-learn, what I wanted to show is that it's pretty easy to swap in and out different models. So I'm going to swap in the lasso model right here, and you'll see we have slightly different values. And if I look at my test metrics, it actually performed worse, right? My test metrics was a little bit lower than the linear model. And again, same thing, we could plug and play with a ridge regression or an elastic net. And same type of idea. You can see that this actually matches up pretty closely with the other values. So just for completeness here, let's actually load in a random forest. Import the random forest regressor, and we're just going to use this random forest regressor instead. So these random forest tree-based algorithms can capture more nonlinear effects, and we can actually see that in my test R squared has gone all the way up to 0.97. My MAE and MSE have both gone down, and we were able to really capture those nonlinear effects in my model. Um, and that's pretty cool, I think. So from there, we could then, what should I have done? I should have done model and metrics. It returns model and metrics, right? Yeah, model and metrics. I should have done, I'll go back and clean this up after class. I should do model and metrics equals that. Yeah, because now from here, I can then look at my model dot feature importances. Or I guess I have to get it out of the pipeline. I'll do that as an exercise for the reader. Yeah, long story short, the beauty of kind of what we want to start talking about when we get into machine learning is know your steps. You have to pre-process your data, try different algorithms, both linear models and tree-based algorithms, evaluate your models against different metrics, and then select which model is best. So for example, I may say the random forest is the best model here. Let's use this in production to predict against my cars. And now we move into that MLOps lifecycle. Now we're going to deploy this random forest and start calling it a day. I only have about 20 minutes left. So I'm going to dive into logistic regression. But it's going to be very, very similar. Once we understand the workflow and the pipeline, pre-process, train, and evaluate, it's going to be very similar. The only thing that's different with classification models is that instead of using the residual as the core error for our metrics, we're going to be using true and false positive rates. Basically, your F1 and not F1, but your type 1 and type 2 errors. So let me just kind of throw an introduction to classification down in the next 30 minutes, and then we'll be out of here. I used to have a pre-built function to do all that for me, but like I said, I lost it. This is the most important part. So if you were online and then hopped, I was going to say, hopefully, you'll learn something if you watch this last 30 minutes. All right, so same kind of idea. We're going to be importing a whole bunch of data, and then I'm going to do some stuff at the bottom. Actually, let me not. I'm actually going to start importing classification report up here. Cool. You'll see what that classification report is in a second. All right, so let's look at our data set. For a classification model, remember our target is going to be a binary data. It should be a binary category. Sometimes you can have a classification model that has more than two categories. That is known as a multi-class classification problem. So let's have a quick look at our data. Again, it looks pretty good. We have a lot of numeric data. I'm just going to confirm that we only have two types in the churn column because that's going to be our target. So yeah, we only have two columns, 0 and 1. We only have 200 rows and only 58 people that churned. So we have a little bit of class imbalance here. Again, you really need to have more data and a significant amount of what you actually want to predict. So we only have 58 rows to find patterns in to predict if someone churns or not. So there'll probably be a lot of noise in this data set. For our data set, you may be wondering again, why are we sticking just with these columns? Same kind of idea as before. If I look at my data frame and look at the correlation, I'm going to do cores equal churndf.core, and we can look at our heat map. And notice that it's the very same workflow, right? Whether it's a regression model or a classification model. So we have all of these values here. Something to note is that we actually don't have that many negative correlations. One thing we can do is if I look at my cores for churn, it'll actually give me the values here. We can take the absolute value of them. Nope. Yes. All right. And then sort them. Let's use pandas sort. And I'm going to do ascending equals false to sort them descending. So there we go. So looking at predicting churn, none of these features really instill that much confidence in me. A lot of the correlations are pretty low. But if you're wondering why they selected tenure, age, address, income, education, employment, equipment, those are all going to be pretty up here near the top. Tenure, employment, age, equipment, address, and then what was the other one? That's the one. Ed still got 20 correlation, so that's not bad. I guess income is probably the lowest correlative feature, so you probably don't need to include income, but they kept it anyway. All right, so now that's why we did our feature selection, right? That was our first part of our pre-processing. So here's all my numeric features, and we should be able to convert those to arrays if we wanted to, run them through a scaler just like we did before, generate our train test split. So fun fact, the scaler typically happens after the train test split. What we're seeing here is actually a little bit of data leakage. Information about the test set was leaked into the scaler before we split it. So that's something to watch out for. And that's why I like pipelines in scikit-learn, because we can do our train test split and then do all of our pre-processing steps within an organized pipeline. Scikit-learn will make sure to take care of all of that for us. In fact, let me actually just pull up a link so I don't lose it. Uh, pitfalls. I love this. So like the pitfalls of training models, and the number one most common pitfall is inconsistent pre-processing. So again, that is where you use test data in your scaler or some other example for that, right? So again, best ways to do this, data leakage, we've talked about that today. Data leakage and pre-processing, all that good stuff. And so again, the best way to do things typically is with a pipeline. Let me see if it yeah, there you go. Alternatively, we recommend using a pipeline, which makes it the easiest way to go. So I'll share this link as something to read on in your own time. All right, let's just run through this notebook though, so we can get to what I want to show you. Again, with the logistic regression, it's a linear model for classification. Ignore the fact that it has a regression in the name. It's a linear model. It's from the linear model family, and it solves a classification problem. It'll predict the probability of belonging to a specific category. And again, we can see that with this predict proba function. This first row had a 74% chance of belonging to class 0. They did not churn, and a 25% chance of actually churning. This person down here had a 74% chance of actually churning. So there's multiple different ways to evaluate um, a logistic regression model or classification model. I like this one. This is kind of interesting. It's not actually to the model itself. It's looking at the feature importances of your columns. As long as your data is scaled, you can use as the coefficients for comparison of features for linear models. But it's actually funny because it shows what we said earlier. Income as the zero lowest amount of like input. It's the least important feature, and we know why. It's the least important feature because it doesn't correlate well with the target. So again, you could probably drop the income feature and call it a day. Um, in terms of evaluating a classification model, there's a various metrics. Log loss is honestly the most complicated one to use. It's a good one. I like log loss because it puts one number on how good your model is. Remember, with the classification model, there is no residual really. So there really is no R squared, MAE, MSE. We have to come up with new metrics. So log loss is one metric. It's pretty complicated though. So instead, let's look at the classification report, which again, I imported up here at the top. Let's do our Y test and our Y hat prob. Or is it just Y hat? Probably. Great. Oh my God, I gotta print it. Print the classification report. There we go. So this is what our classification report looks like. This is what I said. Typically with classification models, our root metric is going to be in type 1 and type 2 errors. Let me also grab the confusion matrix. Where are we? Let me plop it. Oh my God. I hate this autocomplete. Great. So here's kind of my type 1 and type 2 errors. So when we start looking at the top left corner, this is going to be the number of people that did not churn that we predicted did not churn. So that's success. That's what we want, right? So we had 25 people who did not churn and we predicted them all not to churn. So that's great. Down here, this 4 number, this is the number of people that did churn that we predicted to churn. So not really that great. If we look at this number right here, this 11, this is the number of people who churned that we predicted did not churn. So that's going to be a type 1 error, I think. You predict you're not pregnant when you actually are. No, other way around. You predict, you predict you're not pregnant when you actually are. I think that's a type 1 error. A type 2 error is where you predict you are pregnant when you're actually not. Or like again, this comes back to like if you remember COVID test. I loved explaining this during COVID because it was all easy because we were all doing it all the time. If your COVID test says you don't have COVID, but you actually do, that's a type 1 error. And so the idea is that you had to take two tests because the probability or the likelihood that two tests would both come back with that same error is pretty low. So that's why you need to do two COVID tests. Same thing why if you pee on a stick while pregnant, you need to pee on a stick twice just to confirm that you are and that it's not just a false positive or a false negative. So this is actually a pretty bad model if I'm looking at it. We have, and again, that's why this number loses some sense. Like with log loss, the lower is better, but I don't know how you're supposed to know that. So you want your log loss to be as close to zero as possible, and it's typically between 0 and 1. So this is not really that good of a metric or a model. But if we look at some of the outputs of the report here, we can see again, this is not a great model. We're 4 out of 15 for predicting churn. And if I look at my report down here, precision and recall, that's just your type 1 and type 2 error. And then your F1 score is the average. So I typically look at F1 score the most. And again, this is going to be between 0 and 1, where 1 is higher. So my F1 score for my target class is only 0.4, which is not great. So again, pretty tough model here. It wanted you to do a bunch of other things, which I'll do a couple quick examples of so I can get to what I want to show you. Great. Again, I have all of this in my GitHub if you want to see it. I'm going to do part B here. So part B, it basically said, let's add wireless to our feature set and see how good the model is. And if I look at wireless, if we go back to my correlations, wireless actually correlates not well, but a little bit better than something like income. So we should actually see some benefit by including wireless. Oh, I forgot to save off churn DF as churn df equals churn df orig dot copy. Let me just blast this through real quick. And let me add in my little classification report and confusion matrix down here at the bottom. All right, so when we start looking at our new model here, I thought this would be a little bit better. Print log loss. Log loss equals that. Let's see if that works. We also need to calculate y test and y. We need to calculate y hat. So then y hat is equal to lr dot predict on x test. Yeah, I think that'll work. Uh-oh, it's mad at me. Go on, kernel, you crashing on me now. So annoying. Let's see if my kernel come back alive.
In between, I just comment that I find usually the log loss kind of uninforming to a person, but it's basically it's amount of entropy. So the higher the number, the more entropy, which means the more randomness. So the higher that is, the worse the model, I guess.
That's gonna be the model worse then? I can't remember. I was hoping
Yeah,
to get a
the
difference
higher
in
the number, the
my.
model is worse because of the greater amount of entropy. That's
Yeah,
basically a form of entropy.
I was hoping to get different values in
That's why
my.
it's also known as a cross entropy, a
Yeah, I
binary
was
cross
hoping.
entropy.
I'm not sure why I'm getting
What are you doing? I see.
different values here. That's all right. I was trying to get different values in my output report, but I guess that's
Why
why
not do
you
log
did the
loss
log
now with
loss.
y hat? Does it have a y prod?
Oh,
No,
y
it's
hat. I did
fine.
my y hat backwards. Y hat with no underscore. There we go. So we can see we did make the model worse. So as Karen was saying, our value has gone up for log loss, which means that our model is worse. Remember, the higher the log loss, the worse your model. And if I look at the actual outputs, my model is also worse. I'm looking specifically at my confusion matrix. We now have 5 folks who we predict churned that didn't. Contrast that to my last model where we got all of the non-churn people correct. So you'll actually notice that my precision went down, as so did my recall, and my F1 score went down to 0.71 and 33. So my F1 score went down, my accuracy score went down, my log loss went up, and my confusion matrix looks worse. So in general, we made a worse model. So don't do that. And again, that's kind of the exercises for the rest of these. They want you to start playing around with different features and see how they change the model performance. But real quick, um, I wanted to do the same thing um, as I did in the linear regression. If I have time, I'll come back and wrap up another example or two of this one. But this should be pretty quick. If I just copy the cell and then make a new one below it, if you wanted to do, oh my God,
I guess
how do I
I,
make, I
oh,
hate,
what are you trying?
I just, no, I just hate this UI. So let's say I wanted to look at number, like E. What happens to log loss if we remove income and employee? So let's do that real quick.
I was going to suggest that it'd be interesting to see the proportion of the two classes. Churn might be a lot less common than not churn,
It is,
in
yeah.
which case
Churn
it's going
is,
to, which case
yeah.
most models are going to bias towards the majority class.
Yep. That's why I mentioned at the start of this exercise too. Yeah, it's that it's we have a bias. We have a bias based on our class size. So if we remove income and employee as well as the wireless, my log loss is still pretty bad and my model is still worse. So doesn't really help anything. But you can compare these values. We got the value of 6529. Hopefully that's what we get, 6529. So yeah, we made all of our models worse. I think the only one that makes our models better is if you remove the feature equip. Let me try that. So we'll do one more here. Um, oh my God, how do I make a new cell? New cell. Oh my God. And move it up. So let's try, let me look at D real quick, which is what happened. Again, this is the importance of feature selection is what I want to tackle here. And then we'll end by making our little pipeline again. So let's remove equip, and I'm going to remove wireless again. And if all goes well, we should have a better model. Yeah, so we have a better log loss. It's gone down to 5.3. But if we compare this to my original one, my F1 scores and my accuracy haven't really improved that much. 82, 42, 72. So yeah, we're lower. We got lower F1 scores and a lower accuracy. So basically all this implies is that my probabilities are a little bit better, but my actual predictions of 0 and 1s like aren't that great. So this just means we're more confident in predicting churning people to churn. So again, up to you. This is where it comes. It's really hard as a data scientist and as a machine learning engineer depending on the metrics we're looking at, if I only look at F1 score and accuracy, this is an objectively worse model than the one that includes the equip. But if I just look at log loss, this is a better model than the one without equip. So again, this is where you, as the data scientist and the machine learning engineer, needs to make a decision, right? What is your model that you're selecting? So probably I would dive deeper into some visualizations, some feature importances, and some other metrics to help me come up with a tiebreaker. But that model selection is a really important piece of the ML pipeline. All right, last thing I'm gonna do, I'm gonna go back to ChatGPT. Make me a similar thing for a classification model. And then here is the starter code. I'm gonna give it the one from the multiple linear regression that I edited, so it doesn't have, so I won't have to go back and edit it. And we'll see what it comes back with. I'm probably not going to do rock curve. Oh, it is doing a rock curve. All right. I shouldn't have included that predicted versus actual plot. This looks pretty good though. We'll just change the feature list here and then all the accuracy scores and then it's doing a rock curve. Cool. I'm gonna get rid of this predicted probability versus actual. So let me drop this in here. What a fun little cell here. So let's see how this would actually work. Again, same deal. We don't need any of the k-wargs, and we'll just leave the model class as it is, I guess. We have all these metrics, looks good. The rock curve is another way to visualize the probabilities. So as you'll see for a classification model, we want our probabilities to actually be good at predicting churn or not. So this is a way to visualize that. And it also looks at the true and false positive rates. So long story short, you want your rock curve to look as much like an elbow as possible. You want it to be as up and then to the right as possible. So this also makes a metric called AUC, area under curve, from your calculus days. That's also a single number that can be used to declare how good your model is. All right, so let's see if this works. I need to update my features. Let me grab my features. All my features are numeric. So I'm just gonna plop these in. And again, this is also where we can mix and match and add in like what was the other one that we added? It was like I forget, but you can add in some of the other ones. Oh, equip, right? Equip. Great. And then we don't have any categorical features, so we can leave that as an empty list. And then this should all kind of work its way through. We don't have any quargs. And then train and fit the model. Boom, boom, boom. All right, so let's see this in action and then we're done. So you're so close. So let's pop back to the multiple linear regression. You can see how we did it. Let's do some imports and then we'll do some, we're not gonna do, let's do our logistic regression. And from there, maybe we'll also do a random forest. From sklearn.ensemble, import a random forest classifier. Oh my God, I hate this autocomplete with a burning passion. All right, and then we should be fairly easy. We know what our target is. Um, our target is just going to be churn. And then we know what my churn DF, I guess the word churn DF a ridge. And I'm going to mix this up a little bit. I'm going to grab my features here. So I'm going to say features equals this list. And then I'm going to just select those columns. So we grab our features, we grab our target, and then we should be able to run it through our model. And then my function is called evaluate classifier. And if all goes well, we should get an alpha. Whoa, beautiful. All right, so this is my little logistic regression. Looking at the classification report on the test set, we can see our accuracy is 0.78. F1 score is still not that good, 8647. It's a little bit different from what you saw before, probably because I added in a column and we also scale our data in the pipeline now. So this is the better way to do it. Not too much signs of overfitting. You can see the full machine learning pre-processing pipeline here. And then we have our visualizations. Not sure what this, oh, that last one was supposed to be the, maybe I will bring it back. That little predicted versus actual plot. Why not? Oh my God. Where are you? Dumb. Let's make sure that works. Sweet. Oh, yeah. I don't know why they made that graph. That's so dumb. I'm gonna get rid of it. I'm running out on time because I got a meeting at the bottom of the hour. Let's do subplots 1, 2. Yeah. All right, so my raw curve doesn't look that great. We should go further up to the left and then over to the right, but at least we have something to look at. And we have the log loss. So this isn't great, but the beautiful thing again is that it's reproducible, right? We can make our model a random forest classifier or a tree-based model. Again, logistic regression is a mathematical linear model with an equation. Random forest is a tree-based algorithm that uses basically if-else statements to solve its problem. A couple interesting things coming off the graphs here. First, we suffer from overfitting. Our model is identifying almost perfect accuracy on the training set, which does not maintain truth with the test set. So the test set is having way worse metrics. Looking at my graph, my awk score is lower, my log loss is higher. So this is a worse model, this random forest model. So maybe we could then give it something like, I only want to have it go with 20 trees to reduce overfitting. What is it? What is it? N trees? Oh, N estimators. Thank you, auto. I've been hating on the autocomplete all day, and here it comes. So yeah, it's still worse, but yeah, that's really bad. So yeah, anyway, the random forest is worse than the logistic regression in this case, but at least we were able to quickly compare two models. So at the end of the day here, you run through all of this work. You train different models, pre-process, train feature selection, pre-process, train different algorithms, evaluate your models against each other using different metrics, select which model you want to keep. So maybe I like this model the best. Then we save that model, deploy it into production, and then use it for inferencing in the rest of our MLOps pipeline. There's different ways to save the model, but we'll review that, I guess, next week.
So your random forest classifier, you might do better with eliminating overfitting by limiting the number of the depth of the trees.
Yeah. So you
When they
can
go when
remove,
they go all the way down as far as they want, then it really starts just memorizing the training
yeah,
data.
you can minimize max depth and num of estimators. And we'll get into kind of this. This is known as hyperparameter tuning. How can you change the different characteristics of your model? With linear models, there's really not that much hyperparameters to tune. It's just an equation. There's only one answer. We've talked about how with a linear model, you get a one equation and one result. But for tree-based models that are based more on randomness and other things, it's possible to train the exact same model, but get different results, right? If you don't standardize that randomness. Again, that's also included on the pitfalls here, is controlling the randomness of your models. And again, tuning some of those hyperparameters can also result in a different model with different performances. This is why we currently recommend utilizing full MLOps platforms to track all of your experiments over time. If you're curious, we use a tool called MLflow, which is an open source modeling way, open source developer platform to basically keep track of all your different experiments and runs and make things as reproducible as possible, right? Again, if I make a model in a vacuum and no one knows how I made it, it's not going to be that useful to an organization. So try and keep your things transparent and reproducible as much as you can. All right, this was a lot. I know I went over a lot here. I'm going to upload all these notebooks into my GitHub. Big things to keep in mind: regression versus classification, predict a numeric value versus predict the probability of belonging to a class, model evaluation for classification models, type 1, type 2 error, F1 score, log loss. And then you should also know the full modeling paradigm: feature selection, pre-processing, training your models, evaluating your models, model selection at the end of the day. We're going to keep practicing this over the next 3 weeks. All week 8 is a lot of this. And then during your capstone project, you'll also be building models and visualizations as well. Hopefully, this won't make next week be as crazy. Again, week 8 is going to go over a lot of this as well in more detail. So looking forward to that. Only one discussion forum for week 7, so please participate. I will see you online and in the forums, and have a great rest of your week.